Welcome, dear math loving students. I once again welcome you. This I want to share you one more lecture, video lecture on this Riemann integration. It is lecture number 10. आज का लेक्चर जो है मैंने इसका हेडिंग जो दी है बैकग्राउंड ऑफ डिफिनीशन ऑफ रीमान इंटीग्रेशन. इट इज एक्चुअली द basic definition of Riemann integration, where from a Riemann integration generated. It is definition and how you define the lower Riemann sums, upper Riemann sums, which are also known as Darboux, this Darboux sums. On the basis of those Riemann sums, lower Riemann sum, upper Riemann sum, the concept of Riemann integration is generated. But that is very important. That is why I have given the heading, it is the background of the definition. Once you understand it, you can fully understand the definition of Riemann integration. तो एक्चुअली अगर हम पहले ही आपको बताते हैं रीमान सम क्या है, लोअर रीमान सम, अपर रीमान सम, तो ये आपको थोड़ा डिफिकल्ट लगेगा. तो इसलिए मैंने आपको इसका बेस बनाया बाउंडेड से, लोअर बाउंड, अपर बाउंड, एलयूबी, जीएलबी, देन व्हाट वी मीन बाय बाउंडेड. तो रीमान इंटीग्रेशन में जो भी आपका क्लोज्ड इंटरवल होगा, आप जिस पे हमें काम करना है फंक्शन का, उस पे बाउंडेड होना जरूरी है. तो आपको बाउंडेड अबव, बाउंडेड बिलो का कॉन्सेप्ट और बाउंडेड का कॉन्सेप्ट हमने ऑलरेडी दिया है. देखो हम कैसे इसको स्टार्ट करेंगे. अगर आप इंटरेस्टेड है, we consider a function fx on closed interval ab. Mathematically we say this f is a function mapped from closed interval AB into the set of real numbers. It is a terminology language of this, where we assume where f is bounded, it is bounded, real valued, it is real valued, continuous also assuming f of x is non-negative. That is, we are taking it as graph above x-axis. For your just to understand the definition, you see, if we are interested now, we want to find out area bounded by lines x is equal to a, x is equal to b, y is equal to 0, and graph of y equal to fx. इस तरह ये जो आपका x इज इक्वल टू a है, ये लोअर बाउंड है f का, इसमें ये अपर बाउंड है मिनिमम मैक्सिमम ऑफ द क्लोज इंटरवल, ये y एक्सिस है, ये है आपको y इक्वल टू fx का ग्राफ. अगर आप चाहते हैं टू फाइंड आउट द एरिया बाउंडेड बाय दिस, आप कहेंगे तो ये तो हमने किया भी है, कर भी सकते हैं. व्हेन यू फाइंड आउट द एरिया फ्रॉम point A to point B, x is equal to A to x is equal to B, you use the concept of definite integral. That is also known as fundamental theorem of integral calculus. But that is the consequences of this Riemann integration. वो पहले Riemann integration का concept define होता है, Riemann integration क्या है, lower sum, upper sum, उसके बाद हम fundamental theorem of integral calculus with the help of Riemann integration करते हैं. तो पहले ये नहीं आया. आप मान लीजिए आपका ये है ग्राफ, मान लीजिए ये है आप ये निकालना चाहते हैं इसका ग्राफ, दिस इज योर y इक्वल टू 0, ओके, दिस इज योर x इज इक्वल टू a, this is your x is equal to b line, this is the graph y equal to fx. This curve continuous bounded between xa and xb and also real valued है, हमने assume किया fx ये x axis से अपर लाई करता है। ये ग्राफ आप निकालना चाहते हैं इसका, ये एरिया you want to find out, you want to find out this area, what is this area hold under between the this curve between y is equal to 0 between x is equal to a। ये एरिया आप निकालना चाहते हैं इसका, ये वाला एरिया, इसका नाम मैं रखता हूं a, सारा एरिया जो है ये एरिया आप निकालते हैं। नो डाउट यू विल से दैट बाय द फंडामेंटल थ्योरम ऑफ इंटीग्रल कैलकुलस और डिफिनिट इंटीग्रल कॉन्सेप्ट यू कैन से इट इज इंटीग्रल a to b fx dx। ये भी है, लेकिन ये कहां पहले ये आया या ये? Actually, the first is concept of Riemann integration, and with the help of Riemann integration, we derive fundamental theorem of integral calculus। उसके बाद आप कह सकते हैं इसके मदद से हम निकालेंगे। पहला क्या है आप? पहला है Riemann this integration। अब ये कैसे हम निकालेंगे? तो इसका निकालने का तरीका है, मैं थोड़ा यहां आउटलाइन बताता हूं, फिर मैं आपको ये शेयर भी करूंगा। हम कॉन्सेप्ट ऑफ जो हमने इससे पहले डिफाइन किया था, क्लोज्ड इंटरवल का पॉइंट्स ऑफ पार्टीशनिंग पॉइंट्स, इस क्लोज्ड इंटरवल ए बी को हम पार्टीशनिंग पॉइंट्स लेते हैं x नॉट लेस देन x1 लेस देन x2 लेस देन xr माइनस 1 लेस देन xr सो ऑन लेस देन xn when this is your a initial point, this is your b। इसमें हम इरेक्ट करते हैं रेक्टेंगल्स इस तरह। अगर ये आपका ग्राफ है, ये आप मान लीजिए इस तरह जा रहा है, ये आपका पॉइंट है यहां पर a, this is b। आप जब ये पॉइंट्स यहां पे लेते हैं, इन पे आप, ये x0 है, ये xn है, यह आपका x1, आपने इस तरह रेक्टेंगल एक लिया, आप समझ लीजिए थोड़ा, ये बना रेक्टेंगल, ये दूसरा रेक्टेंगल, यहां भी एक आप बनाएंगे इस पॉइंट पे x2 पे, ये इस तरह रेक्टेंगल जाएगा, ये रेक्टेंगल, ये आएगा इसका यहां तक पॉइंट है, ये इस तरह। आप देखिए इसमें कुछ पार्ट्स है, कुछ रेक्टेंगल्स बनेंगे इसमें जिनका पार्ट जो है वो बियॉन्ड लाई करता है, बियॉन्ड द कर्व, और छोटे वाले रेक्टेंगल्स, ये रेक्टेंगल जो है इसका नाम हम लेते हैं R1, इसके एरिया का। ये रेक्टेंगल जो है इसका एरिया लेते हैं हम S1, यह आएगा R1 S1, यह आएगा R2, यह है आपका S2। इसी तरह आप जाएंगे, अगर आप यहां पे जनरल लेंगे इस तरह XR माइनस 1, यह है आपका XR, यहां आप इरेक्ट कर सकते हैं रेक्टेंगल, यह है आपका रेक्टेंगल, इट इज फुल्ली लाइंग विद इन द कर्व, एंड दिस you will construct, you will proceed this onwards, you will get another rectangle. In layman's language, I will say this is larger rectangle, okay, this is smaller one। larger rectangle का एरिया मैं डिनोट करता हूं RR से, स्मॉलर जो है ये वाला, इसका एरिया मैं डिनोट करता हूं SR से। When you put R is equal to 1, this is this rectangle. When you put this S1 is this. When you put R is equal to 2, this is this, this is this. आइडिया हमें यह मिलता है कि इसमें ऐसा होता है कि जो नीचे वाले छोटे वाले रेक्टेंगल्स है वो ग्राफ के नीचे लाई करते हैं, जो हमें जरूरत है, रिक्वायर्ड एरिया जो हमारे पास जरूरत है, ये वाला एरिया, इसके जो छोटे वाले रेक्टेंगल है दैट लाई एंटायरली विद इन द ग्राफ, रिक्वायर्ड ग्राफ, जो हमें जरूरत है, रिक्वायर्ड एरिया। लेकिन ये वाला रेक्टेंगल जो है ये आउटसाइड लाई करता है। अब देखना है जो हमारे पास कॉन्सेप्ट है रीमान इंटीग्रेशन का, हमें एरिया निकालना है। वो एरिया मैं अभी बताऊंगा। वो एरिया लाई करेगा लेस देन दिस। ये बड़े वाले रेक्टेंगल्स जो है, एरिया हमारा है लेस देन सम ऑफ ऑल द रेक्टेंगल्स, बट एट द सेम टाइम इट इज ग्रेटर देन the sum of all the rectangles that lie entirely within this curve. This is the concept of this Riemann integration, sum of lower Riemann sum and upper Riemann sum. हाँ, ये मैं बता के रखूंगा। अगर आपने पॉइंट्स ऑफ डिवीजन जो है, पार्टीशनिंग पॉइंट्स, इन पार्टीशनिंग पॉइंट्स को आप इंक्रीज करेंगे, इतना इंक्रीज करेंगे टेंडिंग टू इन्फिनिटी। when n tends to infinity, n stands for number of partitions of the closed interval AB. When this number of partitions you take large up to infinity, the area this larger जो है rectangles R ये decrease हो रहा है, और ये जो है SR sum of rectangles, lower rectangles, they are this increasing. These are decreasing, those are increasing, and our area will lie. Sandwich principle यहाँ पे यूज होगा, लिमिट कॉन्सेप्ट यूज होगा। our area will lie within the sum of all the larger rectangles and the sum of all the lower rectangles, smaller rectangles. That is the concept of this, what is called lower Riemann sum and upper Riemann sum. So इसमें क्या इन्वॉल्व होता है, हमारे पास ये एरिया है सारा, ओके हमने इसको डिवाइड किया है, पार्टीशन किया है, पार्टीशनिंग पॉइंट्स, जो पहला वाला लेक्चर आपको है वो देखिए आप। पार्टीशनिंग पॉइंट्स क्या हमने दिया वहां पे, रिफाइनमेंट ऑफ द पार्टीशन। इफ यू डू नॉट रिवाइज दैट, इफ यू डोंट गो टू दोज लेक्चर्स, you cannot understand it. Be patient, you just understand what we did there, and it is now the concept of Riemann sum, upper Riemann sum and lower Riemann sum. We take the partitions here, x0, x1, x2, x3, then we erect the rectangles. Some of the rectangles go outside this, and some of the rectangles go inside the area of this, and we take the this area lies between the less than the rectangles that whose part lie outside the curve, and greater or equal to the rectangles whose sum lie this under the graph of the curve. This is the lower Riemann sum and upper Riemann sum. You just remain with me. I will explain the figure and I will write something so that you will understand. Again, be patient. हाँ गाइज, हम आपको यहाँ पे अब बैकग्राउंड देते हैं कि ये मैंने कहा यहाँ पे, नाउ टू डिटरमिन द एरिया बाउंडेड बाय द लाइन इज x is equal to a, x is equal to b, this is x is equal to a, x is equal to b, this is the graph, this is the graph of the function y equal to fx. So this is bounded, whole is bounded between a and b. We have to find out this area. How we go? Graph of this, we assume that f is a function mapping from closed interval a b to set of real numbers. You have the concept of function, so there is no need of explaining this once and again. Also we take, it is bounded fx non-negative greater or equal to 0, so we assume graph is upper side for all x belongs to closed interval AB. And further we assume f is continuous also, there are no gaps or breaks. We use the concept of partitioning that we discussed in previous lectures. Partitioning of a closed interval, let us choose the points of partition to be x0, x1, x2, xr minus 1. It is a general partition we take, xr minus 1, xr, xn. It is of this closed interval AB, such that in previous case, as we did in previously, x0 is less than x1, is less than x2, that is one is less than xr minus 1, xr. It is this. x naught, this is x naught, x1, x2, x3, x4, xr minus 1, xr, xn. Now what we do with the base, this is when we put r equal to 1 in this, or before that I will write, explain. Of course, f is bounded in each subinterval, because when a function is bounded in whole, it again remains bounded in the parts. So when f is bounded on the closed interval AB, it again remains bounded on this xr minus 1, xr. So it is bounded on I1, which is x0, x1. It is bounded on I2 subinterval, that is x1, x2, x1, x2, means it has the lower bound and upper bound. And we assume now for each r, among r equal to 1, 2, 3, 4, I have explained it, erect a rectangle. We erect a rectangle, capital RR, that lies, part of that lies outside. This is capital R. I will explain. This is a capital R, this rectangle. The part of this rectangle lies outside the curve, which we don't need in this area. Part lies outside the curve, but our area is under the curve. So this is a rectangle whole, capital RR. That means this is R1, this is R2, this is your here, this R3. So these rectangles whose parts lie beyond the curve, beyond the area, and the portion lies within, the portion of these rectangles lie within this area, but some parts lie outside the area. That's why we are writing here. Now for each R among this, erect a rectangle RR. The name of the rectangle is RR, the part of which lies outside also. On the subinterval IR, XR minus 1, XR. There is XR minus 1, XR. When you put R1, this is this. When you put R2, this is this. When you put, so these are the, I have taken here dash, 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 so you can erect so many rectangles between this and between this. Okay. You see, as base, this is base. X, what is the length of this? X1 minus x2 naught. It is the length of this base. Here it is x2 minus x1. Here it is xr minus 1. It is the base. And with altitude such that portion of the graph of f for all x belongs to xr minus xr lies in the rectangle. जो हमारे पास ये ग्राफ है, जो हमें जरूरत है एरिया, और ये एरिया जो है, इस एरिया का पार्ट वो यहां पे लाई करता है. देखिए ये पूरा रेक्टेंगल है ना, इतना हमारा एरिया ये जा रहा है, ये वाला, ये यहां देखिए आप, ये है रेक्टेंगल, कैपिटल रेक्टेंगल RR. हमारा एरिया जो है, एरिया ऑफ द कर्व अंडर दिस, वो इसमें जाता है. यही हम लिखते हैं यहां पे, lies in the rectangle which is possible as f is bounded. It is bounded. In fact, we choose altitude of RR to be MR. To be MR. Altitude we choose. देखो यहाँ पे ये आपका रेक्टेंगल है, ये वाला, ये इतना, इसका जो ये altitude है या ये altitude है, that is capital MR. इसी तरह ये वाला रेक्टेंगल जो है, इसका altitude जो है, रेक्टेंगल का हाइट वो है M1, इसका कैपिटल M2, इसका कैपिटल MR, इसका यहां पे आएगा कैपिटल M. ये वाला रेक्टेंगल, ये है कैपिटल M हाइट, और ये वाला जो है, ये है स्मॉल m, नीचे वाला रेक्टेंगल. ठीक है. सो वी राइट हियर द विच इज पॉसिबल एज f is bounded. In fact, we choose or this to be MR. MR is the LUB, least upper bound of what? Least upper bound of this fx such that x belongs to this. ये इस फंक्शन का least upper bound है. ये मैं थोड़ा यहाँ पे ये करूंगा, यहाँ पे it is a least upper bound of this function fx such that x belongs to this clue. So this is LUB MR. Capital MR is LUB of fx. That means when you put R1, that means capital M1 will be the LUB of x0 x1. इसका LUB क्या आएगा, जो हाईएस्ट जा रहा है वो है ये M1। इसी तरह व्हेन यू पुट R2 M2, इस एरिया क्या आएगा, एरिया यू नो एरिया ऑफ द रेक्टेंगल इज लेंथ इनटू ब्रेड्थ, सिंपल, दिस इज द हाइट, this is the breadth, length of the breadth, length of this, what is length of this, x or minus 1. So means when you find out this rectangle area R1, this will be M1 x1 minus x0. When you find out R2, this will be M2 x2 minus x1. When you find similarly Rn, this will be M times xn minus xn minus 1. These are the R1, R2, capital R1, capital R2, capital R3, Rn. These are the rectangles whose portion lie outside the graph and the some portion lie within the graph. When you take sum of all the rectangles, sum of all these rectangles whose part go outside, what about when you compare the sum of these rectangles and our area of this, area of the curve, area of this function y is equal to fx under x is equal to a, x is equal to b, means our area becomes less than the sum of those all the rectangles, because the portion of the rectangles lie outside the graph, which we don't need. We need this area within this, but part lies outside. So our area in this case will be less than or equal to sum of all the rectangles, larger rectangles. It is sum of all the less or equal to, when you will put a question why equal, where does equal comes, yes, you will understand later on, because when we make the partitioning points to go infinite, when they become large, then these will decrease. The RR जो है this upper rectangles, bigger rectangles, this number will decrease, and the smaller rectangles which we denote by SR, their number will increase, and by the Suki's principle limit concept, area lies between the upper and lower. I will now similarly write about something, this the SR, this is SR here, SR is this is capital SR, means the rectangles whose area lie below the graph. You see about this rectangle, just look here. What about this rectangle, this, it is entirely lying within our area, but this part is missing. This part also is our area, this part is also our area. This is lying entirely within the area, and this one is missing. Let's just look here. This is your SR. This is your SR. S small r. General limit, general interval I take. You see its area. What about its area? This is lying entirely within this graph, but something is missing. This does not come under this. So when you say, what about the sum of all the rectangles which are, in other words, smaller in size, which lie within this, the sum of all the rectangles, the area is less or equal to the area A, is less or equal to the area A, because something remains missing. So area is greater or equal to sum of all the upper rectangles, and the same area is less or equal to sum of all the lower rectangles. So our area is caught between sum of all the larger rectangles and sum of all the smaller rectangles. This is the concept of definition of Riemann integration, and this will generate now what we mean by lower Riemann sums and upper Riemann sums. Once you have understood this concept, don't this jump over that definite integral concept yet. Don't jump over this fundamental theorem of integral calculus that gives you the area between x is equal to a, x is equal to b by writing integral a to b fx dx, until you understand this, because that is the consequence of this. This is the basic. So this you have understood, some of outer sum of all the rectangles, the part of the which is outer. Now we write similarly sum of all the this lower. Then we will explain something more. Let us continue with this. We have already explained कि R1, कैपिटल R1, कैपिटल R2, कैपिटल R3 क्या स्टैंड करते हैं? ये एक्चुअली स्टैंड करते हैं रेक्टेंगल्स whose part lies outside the curve. एंड आपने ये भी देखा कि इसमें जो ये हाइट है, इसका हाइट आता है मैक्सिमम, वो हमने लिया m1. ये जो इतना पार्ट है इसका हाइट है m1, स्मॉल m1, वो हम लेते हैं s1 या sr के लिए mr. देखे मैंने लिखा यहाँ पे, इट इज वेरी इंपॉर्टेंट. नाउ द रिक्वायर्ड रेक्टेंगल्स जो है, रिक्वायर्ड एरिया ए जो है, ये वाला एरिया, ये सारा एरिया जो है, lies in the union of rectangles, in rectangle का union. It may be noted that these rectangles are non-overlapping. ये overlap नहीं हो रहे, otherwise there will be a problem. The required area is A less or equal to sum of these rectangles, because our area lies within and the area of rectangle, sum of the area lies outside. So our area A is less than or equal to sum of all these rectangles, which we can write is R running from 1 to n, capital MR, XR minus XR minus 1, because it is the length, base, length one part of this rectangle, length, and this is the height, MR. So for R1, capital R1, you have M1, X1 minus X0. I have explained that previously. Now we go to the rectangles which lie entirely within the area, You see, again for each R, erect a rectangle SR, whose base is again XR minus 1 XR, and with altitude such that SR lies entirely in the region and where we choose capital MR, the GLB of fx. इसका GLB ये होता है, आप देखिए अगर आपने ये यहाँ पे लिया, दिस इज योर रेक्टेंगल, इसका ये हाईएस्ट पोर्शन ये है, लोअर आएगा ये, दिस वी टेक MR as the GLB of this fx because it is bounded, it is possible, it has the maximum and minimum MR. तो हमने यहाँ पे पहले वाले रेक्टेंगल के लिए M1 के लिए आएगा ये GLB, M2 आएगा सेकंड रेक्टेंगल के लिए S1. अगर हम एरिया निकालेंगे, ये वाला एरिया, ये वाला एरिया अगर हम निकालेंगे, ये देखिए हमने लिखा S1 is M1 into this base into height, M2 is this, Mn is this. The sum of all these rectangles, when we take the sum of all these rectangles, cannot exceed the required area A. Cannot exceed. It is not greater. It is not greater or equal. It is less. It cannot exceed the required area. Because when we find out that area, our area lies this part also. In our area, this part lies when this is not in this rectangle. You find the area of this rectangle. So this. But our area is this. This part does not lie here. That is why we say the sum of all these rectangles cannot exceed the required area A. Therefore, A is our area, required area, this is greater or equal to. Our rectangles lie within this area, but there is something missing in our area. What is something missing? This is missing. It does not come in these small rectangles. This is missing. Okay, this is missing. It is our area. This is our part of area, but it is missing. This is our part of area, but this is missing in this. This is our part of area. It is missing in this. That is why I say our area is greater or equal to this, or this is less or equal to A. So from first and second, our area A is caught between the minimum, this sum of all the smaller rectangles, which are entirely within the graph, within the area, and is less or equal to sum of all the outer rectangles whose part lie outer. It is this capital M or XR minus 1. Now this is the concept of lower sum, upper sum. This is how lower sum and upper sum generated. This I have given you the very important concept. You will use this throughout in our this what is called the Riemann integration. and this is the basic. That is why I have said this is basic. Now there is one thing more very important that I want to discuss with you. If we increase these partitioning points, increase how much? Say you go to infinity, then this this sum of these areas will decrease. This summation will decrease, it will increase. That means both the sums will converge to A, converge to area A when partition n becomes larger and larger, n tends to infinity. It is the concept of limit of sum that you previously in the first instance defined the integral as the limit of sum. Integral as the limit of sum. When the partitioning points increase, then you have the choice. The area is converging between this and this. Your area is A. So this will decrease and this will increase. Okay, I will write this point also for you. Wait. Now finally we have a very important this conclusion. I have given you the full idea of this lower sums and upper sums, not defined yet lower sums and upper sums, but definition is clear. The same is the definition. Finally, I note here, I write a note. We also note that as the points of partition of this closed interval increases, when you increase the points of partition, this is the this is sandwich principle. The sum this upper integral, rectangle, sum of all the rectangles are capital R, R1, R2, R3, sum of all these rectangles decreases, and the sum, this is sum of lower rectangles increases. And when it increases, what happens is both converge to area A. This is area A. They converge to area A as the number of points of the partition tends to infinity. When the number of points of partition tends to infinity, then you have the lower Riemann sum and upper Riemann sum converge to one and only thing, that is the area. So you have understood how this definition is generated. Next, I will give you the definition of what is called lower sum and upper sum. उसके लिए मुझे कोई प्रॉब्लम अब नहीं होगी. आपने समझ लिया कि lower sum is nothing. It is sum of all the rectangles that lie below the this graph of the curve y equal to fx, and upper sum जो आएगा, it is sum of all the rectangles, the part of which lie above the this curve y is equal to fx, and our area जो है that is caught between the lower sums and upper sums. And one more thing is, if we increase the points of partition, they say points of partition tend to infinity, then there is a convergence concept that our area converges to this, both the sums converge to area A. So you will wait, we will be giving next to you the lecture, that will be lecture 11, so it is 10. We will give you lecture 11, that will be the lower sums and upper sums, and then you can go to the theorems. Revise fully this is basic concept about lower Riemann sum and upper Riemann sum. On the basis of this, you are able to solve all the theorems. That will become very easy to you. Thank you very much. I love you if you love mathematics. Thank you very much.